So the last video on the exponential functions will be about the laws of calculations with logarithms. And it is convenient to recall the graph of the exponential function and look at that one. So let us take base a bigger than 1, so we get this picture. Of course, a to the power x, if x is equal to 1, then we get 1. If x is equal to 1, then we get the value a to the power 1 equals a. And again, the natural logarithm was defined by taking an inverse, so we start with x, then we get an realization a to the power x. We call this y and go back again. Then this can be done in a unique way, as we saw, because we see it again. We get x back, but this is also equal to the log of y. Now this gives some important relations that one uses often. So what do we get? If we start with x, so I recall what we did, we get a to the power x, we call this y, and we take the logarithm. We come back to x, so we get the logarithm of y equals the logarithm of a to the power y, x equals x. Of course, x can be any real value. On the other hand, we can also start with a realization y over here. So we go to we take the logarithm, we call this x, and then we put x into the exponent, and we can come back to y again. So we get a to the power x is a to the power the logarithm of y, and we come back to y, and this is now a positive real. What this tells us is also something different which one can use a lot. So I've had two expressions, one which are supposed to be equal to each other, or we want to check that they are equal to each other. Then we can also check whether they are equal if we put them into the exponent. Or we can check whether they are equal by taking the logarithm. And it's just by the fact that we can do these inverse maps. Of course, to take the logarithm we have to make sure that these expressions are positive, so we have to think about that, but it's a good way to check relations now and then. Okay, now it becomes quite easy to derive the laws of calculations with logarithms, so again I want to illustrate this a little bit in a picture. So we get again the exponential function. Say we have two variables x and y and a sum. Now what do we get if we put them in the exponent? So we get a to the power x as a realization a to the power y and a to the power x plus y, and we know that this is a to the power x plus y is the product of these two other things. So suppose now that we start with these realizations. So we go back and we come back to our x, y and x plus y. So what do we get? When we start with x, y and we take the sum, then we end up with realizations where the last one is a product of the other two. If we now start with three, say, values, positive real values, of which the third is the product of the first two, and we take logarithms, then in the same way, what we end up is that the third now is the sum after taking the logarithm of the logarithms of the other two. So this gives us the first law. the logarithm of the product of two, now we, of course, reuse our variable names. So the logarithm of the product of two positive numbers is equal to the logarithm of the first plus the logarithm of the second. Now, logarithm turns products into sums, and taking exponents gives us that the sum is turned into a product. Now the second law tells us that if we calculate the logarithm of x to the power y, that we can take the power in front. I will tell you something about that in a minute. The logarithm of 1 is always equal to 0. Well, of course, if we start with 1 over here, then going back to, so if we have a realization 1, then we come back to 0. So this is immediate. If we take the logarithm of a, the logarithm with base a of a itself, so we have the inverse of a over here, and we come back to 1. So this is equal to 1. It's quite easy. That law is straightforward, and I only have to tell you something about the second law. Now, this is quite easy to infer from our previous rules, and the way to do it is start with x to the power y and rewrite it in two different ways. Now, how can we rewrite it? We can rewrite it in the following way by using this relation over here. No, which one? Yeah, this relation over here. So we replace y over here by x to the power y. So we get x to the power y is equal to a to the power log a of the thing that we had. On the other hand, we can also replace only x. So we insert x over here, and then we get x equals a to the power log a of x. And then, of course, we have to still take this power y. Now we know by calculation with powers that this is equal to a to the power log a of x multiplied by y. And now we use our rule over here. So we have a to the power the first expression equals a to the power the second expression. Then these expressions in the powers must be equal. And this is exactly our second law. So what we end up with is that this power over here must be equal to this one over here. And this is precisely what I've written here. So these things are quite easy to understand once you understand these rules and once you know how to manipulate powers. Now I want to make some other observation, because if you people who recall calculations with logarithms quite well know that I skipped one of these laws, but this law which I skipped is in fact a combination of the previous one. So let us look at logarithm of 1 over x. Now 1 over x can always be written as x to the power minus 1. Powers can be taken in front, so we get minus 1 multiplied by the logarithm of x. So this is minus log x. Suppose that we want to calculate the logarithm of y over x. This is precisely this law that I skipped. We can write y over x as y multiplied by 1 over x. 1 over x can be written as x to the power minus 1, and now we use the first law, namely that the log of a product is the sum of the separate logs. So log y plus log y, log y plus log of x to the power minus 1, we replace it by minus log x is log y minus log x, and this is precisely this missing rule. Now, as a final thing, I want to make a comment on why in the literature most of the cases you see a fixed base. In principle we use base e, so the natural logarithm most of the times. And this is because there's a very natural relation between the logarithm and the natural logarithm of two numbers. So if we look at logarithm of x with base a, then this, what I claim is that this is equal to the natural logarithm divided by the natural logarithm of a. So in fact these two logs differ a constant factor. Now why is that true? It's again a very nice application of the law, these expressions which I wrote on top of this sheet. Again, we rewrite the natural logarithm of x. Now we can replace x by a to the log a of x. So we do it, ln a log a of x. Now again, the second law over here tells us that we can take powers in front. So we get log a of x multiplied by the natural logarithm of a. And this is precisely this statement over here, because we can divide both sides by the natural logarithm of a. Some calculation examples. Log with base 3 of 81. Well, what is 81? Is 3 to the power of 4. So we can take the power in front to get log with base 3 of 3, and we solve that log that this is equal to 1, so we get 4 times 1 is 4. One more example. The log with base 8 of 4 plus the log with base 8 of 16 is, we can take the log of the sum is the log of the product of these two numbers. 4 times 16 is 64. 64 is 8 to the power 2. The power can be taken in front, so we get 2 times log 8, log with base 8 of 8, which is equal to 1 is 2. So many of these things can look complicated, but are quite simple once you know how to manipulate. And the third example is an equation. We want to solve 5 to the power x equals 7 to the power x plus 2. Again, x is in the exponent, and this calls for using one of these laws over here. Now, which one do we want to take? So we want to have these x not in the exponent, but say on the ground floor in some sense. So we take logarithms. Now the easiest thing is always to take natural logarithms. We are able to do it according to these expressions. So we take logarithms, then if the expressions are the same, the logarithms are the same, and vice versa. So we say, well, we take logarithm, and then of course this solution, this equation is equivalent to natural logarithm of 5 to the power x is equal to the natural logarithm of 7 to the power x plus 2. We can take the powers in front, so we get x ln 5 is equal to x plus 2 times ln 7. Now this is a simple equation. You can take all factors with x to one side, and the other remain on the right side, so we get x times ln 5 minus ln 7 is 2 times ln 7, and so we get that x, it's correct, x is equal to 2 ln 7 divided by this expression, but the difference of ln 5 and ln 7 is ln 5 over 7. So what we get is that x is equal to 2 times the natural logarithm of 7 divided by the natural logarithm of 5 over 7.